Hello students. Next we come to the last part of this third module wherein we are looking at the transient analysis of RLC circuit with initial condition. That means up till now we had either seen for the switching circuits, we had either seen an RL circuit, that means a resistance with an inductor, or we had seen an RC circuit where we had a resistance with capacitance. There was no circuit where we dealt with both capacitance and inductance together in this switching initial condition kind of problems. So this particular section is dedicated to those kinds of problem wherein you have a capacitance as well as a inductance in the circuit at the same time. So here in the network of the figure shown below, the switch is already closed and steady state is attained. So the switch is closed and steady state has been attained. At t is equal to 0, the switch is open. Determine the current through the inductor. That means you have to find out how much current is passing through the inductor. So as we always do, we solve it by first writing what is going to be the circuit condition at t is equal to 0 minus. That means just before the switch is made, what is the circuit looking like? So we are having an voltage source, then the switch is closed and we are having a resistor is 2.5 ohms, and then we are having a capacitor, and we know that if the capacitor is charged, because the switch was closed, the capacitor is charged, so it is now an open circuit. And what about the inductor? The inductor, once power has gone through it, it becomes short circuit. So I have to draw that as short circuit. So now I am having two initial conditions here. One is I have to find out what is the initial condition current flowing through the inductor and what is the voltage that has been stored across the capacitor. So I will write it as V0 minus. So both of this I have to find out. Now from this circuit, one thing is very clear. Since this path is short, that means there is no resistance, there is no impedance there, the voltage across this will come out to be 0. Why? Because the voltage across a short circuit path is 0. So one thing I can very clearly write from this figure is that V of 0 minus is going to be 0. That is one of the conditions that I have seen. The second is how much current is going through the inductor which is charged, and from that we can very clearly see that the current that is going through is I0 minus is going to be the total voltage divided by the impedance or the resistance that is there in the network, which is 2.5, which gives me 2 amperes current. Therefore we have found out what is the voltage and current to which it is charged. So you can see that the capacitor is not charged. Now you might be thinking, how can a capacitor not be charged when it is connected to a battery? The reason lies with the fact that there is an inductor here which acts as a short circuit, and because of that short circuit, all the charge that is going to be accumulated in the capacitor is also going to drain out. Why? Because we have short circuited the capacitor. So that is the reason why the capacitor is not charged here. Anyway, we have got the initial condition. Next we have to find out what happens at t greater than 0. At t greater than 0. So at t greater than 0, we know that the circuit is open. So now the resistance is there, but that is now immaterial. There is a capacitance, and then there is a inductor, and we know that if the inductor is charged with some initial current, I will write it as a voltage source, and the voltage source will be such that it is with the original voltage source. The polarity is such that it's in the same, and its value we all know is L I naught. L is zero point 0.5, so zero point 0.5. I naught is 2, so zero point 0.5 into 2, which gives me 1. So let me write straight away here as 1. So this is 1 volt. Why? Because it was L I naught. You can go back, I naught minus. You can go to your notes and you can find that that is what we had studied. You remember this transform circuit? From there we have taken for this one and this one what is the equation. So that is why we have got that. Okay. So let me come back here. So this is what, and Ls is going to be 0.5s, or even I can write it as 1 by 2s, it does not matter, but let me keep it for the time being as 0.5s. Now what about the capacitor? For the case of capacitor, it is going to be, the voltage should be V naught by S. The voltage should be V naught by S. How? Based on what we have studied, we know that it should be V naught by S. It should be V naught by S. But what have we got in V naught now? We have got V naught as 0, isn't it? Here we have got V naught as 0. So we cannot do that. Voltage, if you want to draw, you can draw. I will draw it, for your sake, I will draw it. And the capacitance is 1 by Cs. See, what is C? C is 200 microfarads, which is 200 into 10 raised to power minus 6 farads, which comes out to be 2 into 10 raised to power minus 4 farads, and 1 by C. So 1 by C is 1 divided by 2 into 10 raised to power minus 4 S, correct? 10 raised to power 4 will go up, so I will get 10 raised to power, so from the denominator I will take out this and I will take it to the numerator. And in the numerator I will write it as 10 raised to power 4, and in the denominator it is only 2 into, so it is only 2 into S, where if I take one of the this thing outside, that means 10 raised to power 3 into 10, if I take, then this and this will cancel off to give me a 5 here, correct? To give me a 5 here. So it is 5 into 10 raised to power 3 by, so I can write this as 5 into 10 raised to power 3 by S. What is the voltage here? The voltage with a polarity will be such that it is opposing the original charging voltage. So plus minus we have here. So V naught is 0 by S, which comes out to be 0 volt, and then the circuit is completed like this. Here there is no point in drawing because it's as good as you are having no connection. So this one I will take out, even this one I will take out. So this is smart. My circuit is looking at t greater than 0, and the current that I am trying to look is the current through the inductor, and the current through the inductor will be, let's say, I of S. So therefore now I will try to find out I of S by taking the KVL. So now from this circuit, so from KVL, what will I get? So let me draw the polarities. So the current is following like this, clockwise direction. This will be plus, this will be minus, this will be plus, this will be minus. Okay, and 0 volt as such we can avoid. There is no need to draw this also, but I have drawn it just because we follow the rules, that's all. So now if I'm going to write from front of the element, then I will be writing minus 5 into 10 raised to power 3 divided by s into I of s, uh, minus 0.5 s into I of s minus plus 1 volt is equal to 0. So if I am trying to take I of s commonly, then I will get I of s multiplied with, let me take minus outside also, so 5 into 10 raised to power 3 is 5000 divided by s plus 0.5 s is equal to minus 1. The minus minus will cancel and I will get I of s is equal to 1 divided by, now in the denominator I will have 5000 by s plus 0.5 s, where I can cross multiply and I can get it as 0.5 s square plus 5000 divided by s. If I write this in the denominator, then s will go in the numerator, so I will get s divided by 0.5 s square plus 5000, where I can take 0.5, I can divide both the numerator and denominator by 0.5, so s divided by 0.5, so s divided by 0.5 can be written as 2s, isn't it? Why? Because 1 divided by 0.5 is 2. So I can write it as 2s. So I will write this one as 2s divided by s square and 0.5 divided by 5000. So 5000 divided by 0.5 will again come as 10,000. So plus 10,000, that is going to be your I of s. That is going to be our I of s. So based on this, now taking inverse Laplace transform, I will get I of t is equal to 2 times cos 10 raised to power 4 is here. So 10,000 is 10 raised to power, this is 10 raised to power 4. I have to take square plus omega, isn't it? Omega square. So I have to take the root of that. The root of that is going to be 10 raised to 2, which is actually I can write it as 100. Sorry. So this is the answer. What do you see here? What is to be mainly noted is this is the first time in a switching circuit you are getting a cosine waveform, isn't it? It's looking like a cosine waveform having a correct amplitude. See, what we have basically made out of this one is an oscillator. How? Because now you have got a circuit which is generating, after charging, it is generating a current or a volt which is basically a current which is basically sinusoidal in nature, AC wave. You have got an AC wave. That is why an RLC circuit is basically used for generating waveforms or AC waveforms. Now you might be thinking that then it is very easy, you charge it with 5 volt and then all of a sudden you get this 2 cos omega t, so you keep on getting the power once you have taken the switch off. We can say in that way that yes, it happens like that, but that is only theoretical, because there is no inductor which has zero resistance. So there will be some resistance that will come into play, because of which when you will do it in that way, you will find out that the cosine waveform will slowly die out with time. So you cannot have this circuit completely, but anyway, for the sake of theory, we can study it like that. Okay, so this is how you get the answer. Let us look at another problem of RLC. So here we are having another circuit. The problem is determine the voltage V of t for t greater than 0 when the switch is opened at t is equal to 0 after a long time remaining closed. So here the condition is that the switch is opened at t is equal to 0. Now as we do the problem, we will one by one find the two conditions. The first one is at t is equal to 0 minus, that is when the initial condition is coming into play, what is the circuit going to look like? So this is having 2A, and then the circuit is closed. Okay, the switch is closed, and the resistance and inductance, we will draw it one by one. So the resistance is this, the inductance will be short circuit. Okay, the inductance will be short circuit and the capacitance will be open. Okay, the capacitance will be open, and we are having plus minus V of t. Okay, sorry, plus minus V of t I will not write because this is at, yeah, this is at initial condition. Yeah, so now what is the value that is going to come here? Obviously the voltage drop across a short is going to be V of 0 minus is going to be 0. Similarly, if there is going to be any current that has to go through this 2 amps, it can go directly, it can directly divide, it can go directly through the switch. There is no point for this current to divide anywhere else. It will directly go through the switch. Okay, it will directly go through the switch. Why? Because the switch is offering the least resistance path. So in a way we can write that this current is also going to be I naught, this is also going to be 0. So let me write that this current is going to be I of 0 minus, that is also going to be equal to 0. Now some of you may doubt that, sir, we are having a current source and there are two short paths. So do you mean to say that in the second short path, there will be no current, that is no current will flow through this path, only all the current will flow through this path? Well, the answer to that lies in the fact that, see, the inductor is going to be fully discharged once this switch is going to be closed. So if the switch is going to be closed, both the inductor and the capacitor will totally discharge. Okay, so in a way I could have actually drawn this as open circuit also, because of which the current would have been totally 0. But I am just following the textbook and just drawing it as a short circuit path, but there will be no current flowing through the inductor. That means if this switch is switched on, inductor and the capacitor both will not charge. Why? Because all the current will flow through this switch, no current will flow through this branch. So neither the inductor nor the capacitor gets charged. So the initial voltage and current, both of it is going to be equal to 0. And now, so I will draw this, so I will write this as both I of 0 minus is equal to 0 and V of 0 minus is also going to be equal to 0. So the initial condition is all 0. Now when the switch is open, so at t greater than 0, what is the circuit going to look like? So here we are having a a current source, and current source is 2 amperes. We will write this as 2u of t. 2u of t, this can be, with the switch, this can be written as 2u of t, and the transformation or the Laplace transform of 2ut is 2 by s. Okay, and then the switch is on, sorry, off, so the switch is not drawn. The resistance that we are having is 0.5 ohms. The inductance, I will directly draw. The inductance is going to be 0.5 s, and the capacitance is going to be 1 by 0.5 s, which can be written as 2 by s. 2 by s, and the voltage here is going to be plus minus capital V of s. Okay, now the thing that we have to remember here is we have not drawn the voltage source for both capacitor and inductor. Why? Because the initial conditions are both 0, so the voltage source is always going to be 0. So there is no point in drawing that. Okay, that is why I have avoided that. Now what is going to be V of s? V of s is going to be, it's very simple, V of s is going to be the current 2 by s multiplied with the total impedance in the circuit, because there is no other impedance. V of s is the voltage across this, correct? So it is basically the current multiplied with the impedance, which is going to be 0.5 parallel with 0.5 s parallel with 2 by s. How do we solve this? So 2 by s multiplied with 1 by 0.5, that is 0.5 inverse, plus 1 divided by 0.5 s plus s divided by 2 the whole inverse, which I can again write it as 2 by s multiplied with 1 by 0.5 is 2 plus 2 by s plus s by 2 the whole inverse. Now for adding the fractions, I will take, so this will become 2 into 2s, which is 4s, plus 2 into 2, which is going to be 4, plus s square divided by 2s inverse. So if I take the inverse, I will get V of s is going to be 2 by s into 2s divided by s square plus 4s plus 4, where this s and s will basically cancel off, and I will get 4 divided by s square plus 4s plus 4. Okay, s square plus 4s plus 4. So now if I am trying to take the factors of this one, if I am going to take the factors of this one, I will get 4 divided by, you can use the calculator to find out the quadratic equation and solve this, and you will get the factors as minus 2 and minus 2, which becomes s plus 2 the whole square. So 4 divided by s plus 2 the whole square. And we know how to solve this further by writing that V of s using partial fraction, V of s, which is 4 by s plus 2 the whole square, can be written as 4 divided by s plus, sorry, not 4, a divided by s plus 2 plus b divided by s plus 2 the whole square. B divided by s plus 2 the whole square, wherein I can find this out by cross multiplying. So I will get s plus 2 the whole square, and with a I multiply a into s plus 2, so it is as plus 2a plus b, nothing is going to be multiplied. So from here, therefore I can write 4 is equal to as plus 2a plus b. Therefore from equating coefficients, I will get a is equal to 0 and 2a plus b is equal to 4. Therefore b is equal to, since a is already 0, so b is equal to 4. So as such, it has not changed anything. correct? It has not changed anything. All that has happened is, you know, you cannot further do it into any partial fraction. So in a way, there was no need for doing this partial fraction. Okay, so it is one and the same. The answer is going to be one and the same, which is v of s is going to be equal to 4 into 1 by s plus 2 the whole square. Actually, I should not have done this partial fraction, because here itself I can take the Laplace inverse. Okay, anyway, so taking inverse Laplace transform, I will get v of t is going to be, we all know that 1 by s square is basically t, whereas 1 by s plus a the whole square, the Laplace inverse is going to be t e raised to power minus at, correct? So here I will get this as 4 t e raised to power minus 2t for t greater than 0. Okay, so this is going to be the answer. There is no need for you to do this, because already, sorry, the partial fraction, there is no need for you to do. Okay, you can avoid the partial fraction. Directly from here you can go to this point. Okay, so with these two problems we will finish the section, that is RLC circuit with initial condition. Always remember that when the circuit is short, all the current will pass through that path. We will try to do some other problems in tutorials. Thank you.